Good. My title says astrophysics, but it could be this. Everything I say will apply to everything in physics, I think, and most of the natural sciences. Good. Okay, good. What I'm going to say, I'm a bit of I work in machine learning. It's true, I do work on machine learning, but I'm a bit of a machine learning hater. So you're going to see there's a lot of negative content here. And part of the question is, how should we be using machine learning? I'm going to say that current machine learning methods cannot be trusted, which does not necessarily mean that they're a bad idea. We will come to when you can use things that you don't trust. And I'm going to point out some biases and systematic errors that come from machine learning that are very technical. So there will be an extremely technical statistics aspect of this somewhere in the middle. And I won't properly explain everything, I'm afraid, because there's so much to talk about. But I hope I will appeal to people who want to do some rigorous statistics. I'm going to talk a lot about engineering because machine learning is a good idea in engineering contexts. And by engineering, I mean all of the stuff that makes physics experiments work. So we're going to talk about that. I'm going to talk about calibration and things. And I'm going to talk a lot about causality or causal models at the end. So we will get there. Okay, good. So I wanted to start by just recapping what we've learned in astrophysics from machine learning. Nothing. There's a ton of papers in astrophysics about machine learning that have machine learning in the abstract, and no breakthroughs in astrophysics has come from that literature. Now, that doesn't mean that it won't. When I pointed this out to David Spergel, who's now the director of the Simons Foundation, he was like, it's too early to tell whether it's useful, even though it's been like 20 years that we've been doing this. But anyway, it is concerning that there's a lot of papers with machine learning in the abstract and there aren't many breakthroughs to point to. So then you could go here, what have we learned in science from machine learning? And back when Twitter was a thing, I asked that question on Twitter and said nothing. And the response was machine learning solved protein folding. And I don't know what news feeds you all read, but there was an important result, which is called AlphaFold, which is from DeepMind. And there's a whole bunch of papers about it. The PubMed reference I have there is, I think, the best of the papers, but there's a bunch of papers. And what that project showed is that using a big training set, they were able to train a model that could learn the structure of a protein from the sequence. So they trained it on a lot of sequence structure pairs and then could predict new structures. And this is very important for drug discovery, clinical things, and so on. In fact, it is one of the functional goals of protein folding. But the interesting thing about this discovery, even though this was a very good result, it was very impressive, it worked better than any other system, it literally we learned nothing about how proteins fold from this. So though it had valuable clinical applications, it didn't actually teach us how proteins fold. And that's going to be related to my point. It did solve an incredibly important engineering problem, though, which will also be relevant to our point.
I remember that when this thing was talked about, it was presented as if protein folding has solved.
Yes. Exactly. My point of view is that it doesn't solve protein folding. But of course, there is something interesting about it. One of the things, if you take an information theoretical perspective, which is what we were talking about at lunch, it shows that the sequence does tell you about the structure, which, by the way, was an open question, right? Because in protein folding, it's not obvious whether the fold comes from the sequence or from the folding mechanism. Anyway. Good. I just want to say, I don't want to sound negative on engineering because actually I do engineering. I'm fundamentally an engineer. I build astrophysics projects and operate astrophysics projects and manage astrophysics projects. I work at all levels. I work on instrument calibration. I work on operations of the observatory. I work on data analysis pipelines. I build models. We do optimization and inference, and I do project management. And we have artificial intelligence and machine learning type things in all of these areas except project management, which is pretty stupid because that's the one I like least of these things. Like if you want to replace the human, that's where I want to be replaced. But anyway, I know, we're hoping, we're really, really hoping that ChatGPT will. Anyway, engineering is a really important part of these projects. I don't know how close people in this room are to astrophysics, but astrophysics has remarkable engineering going on right now. We're measuring radial velocities at a 10,000th of a pixel in spectrographs. We're measuring galaxies and quasars at redshift of 17. I mean, it's really remarkable what's going on in astronomy right now. Good, but my important thing for me is that engineering successes are not the same as science successes in the sense that you can build a really beautiful machine that makes very precise measurements, but actually not learn anything important about the universe from it. And vice versa, you can sometimes learn something important about the universe even when your machine is terrible. Like the discovery of the cosmic microwave background was, a very simple object that found the background. Good. I think great engineering makes all science possible. I think that really is true. Like if you think about the discovery, the Copernican principle was really discovered by Galileo, who was the first person to really use a telescope to look at the stars. Like that was a good move. That was a great idea. Take some good engineering, use it for science. Okay, good. Now, I'm trying to be as controversial as possible. First controversial slide. We were talking also about this at lunch. This is the maximal definition of machine learning. There are more minimal definitions of machine learning. This is the maximal definition. The maximal definition is a machine learning method is a method whose capability improves as it sees more data. And then I have a caveat here that it probably has to improve substantially better than the square root of n. Because if you're just taking like the mean of your data, it will improve as the square root of n, and I really don't want to call that machine learning. And the classic machine, and so in this description, a lot of things are included in machine learning that you might not include, like principal components analysis, independent components analysis, support vector machines, linear regression, my favorite. I've written many papers about linear regression, Gaussian processes, and so on. So a lot of things that you might not consider machine learning are all machine learning from my perspective. And contemporary methods are all the things you usually see. Multi-layer perceptrons are the standard for non-structured data. CNNs are the standard for image and video data. And transformers are the standard for text. Now, good. Okay, good. So just to make sure everyone's on the same page, most people in the room already know this, but let me just be very clear. Because I will sometimes talk about features and I'll talk about labels and what goes on, but I'm very interested in features. So the idea is you have a set of objects which has features and labels in this is supervised machine learning. There's also unsupervised where you only have the features. But you have features and labels, and you have some good set of features and labels, and the features might be things like YouTube videos, and the labels might be, this YouTube video contains a kitten. That would be a typical problem in machine learning. That is literally a typical problem. I think that was a challenge problem, actually, that Google set up a long time ago. After they bought YouTube, they set up a challenge with videos and kitten or not. And then what you do is you try to find a function that does a very good job of predicting the labels in this training set, or that finds the transformation from features to labels. So it's a function that takes the features as input and produces the labels as output. And the idea is you give this function immense flexibility. Literally billions of parameters in the current world. And then you predict new labels for test data, for data that aren't in your training set. And there's a deep assumption, which is going to come up again, which is that the test data are somehow similar to your training data. So your training data were relevant to your test data. And you can already see how problematic that's going to be in astrophysics. Physics has different questions in astrophysics, but astrophysics is very much about discovery. So we really hope our new data doesn't look like our old data. So that's going to be a problem right there. Good. Okay, good. So what are the uses of machine learning in astrophysics these days? We got it all. Classification, and there's a lot of dumb classification things, but the smart classification things are when you're in a real-time pipeline and you have to quickly decide what you're going to do. Are you going to send this object to this pipeline or that pipeline? Are you going to send this object to another observatory for follow-up? Real-time things. And it also happens in the ATLAS experiment. Very quickly, the ATLAS experiment has to decide, are we going to store this event or are we going to throw it away? And in fact, they use machine learning in that. Outlier detection. This is a great use of machine learning. It's been very productive in astrophysics. This is a place that's been productive. I wouldn't say any huge discoveries came from it, but it's been very productive to find objects that don't look like other objects, because those are interesting. Dimensionality reduction, that's going to come up later. One of the things that's amazing about almost all astrophysical objects is they all live in very low dimensional spaces. And if you can discover that low dimensional space, it usually helps you. Label transfer, that is a lot of what I work on, where there's some stars that you, for various reasons, you know their properties very accurately. There's a bunch of other stars that you don't know their properties, but you have some spectroscopy or something, some features to work with, photometry, spectroscopy, and you want to transfer the labels. So the labels you've learned the hard way, you want to put onto all the other stars the easy way. That's a problem I work on a lot. That's going to come up again. And then emulation. And this one is very strong in astrophysics right now. The simulation requirements of astrophysics now are very high. Typical cosmological simulation takes weeks to months to run on large supercomputers, and we need thousands of them or tens of thousands of them to do our science. And so we're reaching the limit of what's possible. Yeah? In all over the place, actually. So any data set we have, people have been looking at outlier detection. Like sometimes you have spectra of stars. You're looking for stars that don't look like other stars. Those are interesting. Actually, that's how quasars were discovered, but it was with a human, not a machine learning algorithm. But in time series, we take lots of time series data right now. There's a mission called TESS, which is taking time series of every star on the sky above some brightness. And the outlier detection there has been super interesting. A lot of cool objects have been found that way. But a lot of the methods that work well there are really dumb. They're not like fancy machine learning methods. They're, statistics of the light curve, and it's weird. Okay, good. But this is the kind of place where places where machine learning is being used. Okay, so I want to talk about philosophy for a minute. Philip is a philosopher, so this slide is for you. And there's some words here that you might have forgotten about since college. I think that the key reasons that machine learning makes us uncomfortable as scientists are these philosophical reasons. And the ontology reason is that in a machine learning perspective, you're trying to take data you've got, called your training data, and you're trying to predict things about your test data, and you don't really care how you got there. So you only really care about the data you started with and the data you end with, and you don't really care about any latent structure in between. It's just data to data. So machine learning doesn't really get that there's anything in between data and data. It's just data. In fact, I was working with a machine learning person years and years ago, like back before it was cool, and we were talking about a tension in cosmology between the cosmic microwave background and the large-scale structure. And his point of view was, well, the only point of physics is to make a connection between the cosmic microwave background data and the large-scale structure data. It's just a transformer that transforms you from large-scale structure, or from large-scale structure to cosmic microwave background and back again. So that's how you should think about this discrepancy. Like there's something wrong with your transformer that transforms one into the other. And I was like, no, that's not what we do. We measure the age of the universe and the density of the universe and the baryon to photon ratio and things like that. So one of the things that's interesting is that in physics, we don't think this way at all. This is not the way physicists think. We think there's an electron. Like no one's ever seen an electron. That's not a thing. It's just the electron is like a component of our model that works, and we ascribe a reality to it. So our discussions that we have are all about the latent space, never about the data space. Yeah, well, I don't think the electron exists. So, yes, exactly. I don't think it exists. I am very close to a pure positivist, actually, which is one of the reasons I can work in machine learning, but it does make me uncomfortable when there's no latent structure. Like, at least the electron makes sense in terms of effective field theory or something. Anyway, the other thing that's wrong with machine learning is it has an epistemology behind it, which is a very bad epistemology. The epistemology behind machine learning is that if you hold out data, train, and it predicts the held out data well, model must be good. And I want to just remind you that that's not how we assess the success of physical theories. Like, if that's how we had assessed general relativity in 1915, we would have thrown it away because it was almost impossible to predict anything with that theory. So it certainly wasn't very successful theory. Yeah, well, right, but that cuts the other way. Okay, good. So now I am very much like an interdisciplinary scientist. I work in statistics, I work in applied math, and I work in computer science. So I work in different fields as well as physics. So I'm a big believer in interdisciplinarity, but there's a weird interdisciplinarity when it comes to machine learning. And a lot of people are like, look at how these beautiful methods that people are building. They're building these amazingly successful methods. We should be using them for science. But that depends on this question, which is like, is there a sense in which presenting content to users is in any way like doing science? I don't know. We hope there is, but it's a little weird to say like, oh, TikTok is killing it. I should be using machine learning in my science. And by the way, TikTok is really impressive. I don't know if people in the room use it, but my God, I'd like to meet their team. Actually, one of the postdocs I work with actually did an internship at TikTok. TikTok actually has internships for people who are interested in machine learning, and it's a very successful machine learning company. Say again? All of them are now unemployed. Well, there's definitely, you're definitely on a roller coaster in that industry, that is for sure. And of course, it's possible that the US Congress will make TikTok illegal. That's also, it's very good at predicting what you will watch. It is smarter than you are in that, I can assure you. You don't even have to look at TikTok for very long before it picks up on your trends. It's very fast at figuring out what you want to look at. Yes, I agree with you. I would recommend you try TikTok. You will be surprised. It's impressive. I mean, it's impressive because it's like, I didn't know I wanted to see that, but I did. I did want to see dad jokes about skateboarding. Actually, the funny thing is that the most successful machine learning companies, by the way, are placing ads. But we all know that the ads we see on the internet are horrible. There's such bad ads, but apparently it makes a lot of money. You know, also all that spam you get, that also makes a lot of money. You know that spam and ads on web pages make a lot of money. And you might, every time you look at those things, you're like, who would ever click on any of those things? But it makes a lot of money. So you're wrong, and they're right. Yeah, TV ads too, yeah. Okay, good. So now I'm gonna say a lot of things that are very situated in astrophysics. You know, not who here would call themselves an astrophysicist? Nice, I've got one. Okay, fine. So what's the difference between? I mean, these are very astrophysics-y slides, but let me just say. The main difference between astrophysics and physics, there isn't that much difference, but the difference is that in astrophysics, we just get what we get. We open up the telescope, we receive the photons we get. So our experiments are not very controlled in astrophysics. We are stuck with dirty, noisy data that you can't design a better star. Like if you want to measure some line in a star, you don't get to design your star. You just look at the stars you have available, you choose the best one. That's it. So the sense in which astrophysics is different from physics is that it's very, there's a lot of things out of our control in astrophysics. It's not like measuring G-2 for the muon where you can control the whole setup. Yeah?
So something like Atlas you would consider astrophysics?
Oh, right. Yes, ATLAS is actually oddly closer to astrophysics than most kind of controlled physics experiments. Where you have like dirty collision. I mean, if you had an electron-electron collider, it might be very different. But when you have, just because electron-electron has a smaller, much smaller phase space of things that can happen. I mean, I guess I shouldn't say that in front of particle physicists, but yeah.
So I've always considered myself a particle. This is by your definition, definitely astrophysics counts because I work on dark matter. I don't control when the dark matter comes.
Exactly.
And it hasn't come yet.
Right, yeah. That's right, and you're very subject. No, and you're right, and so for instance, even if there was a high cross-section of the dark matter, you still might not get an answer because there might be like phase space substructure that's killing you. I've thought about that problem a lot. I'm not talking about my more traditional science domain, but one of them is dark matter. I work on dark matter, but I work on it from an astronomy point of view. Anyway, astrophysics in physics is very similar to like earth science or planetary science or heliophysics, where you just have a system that you don't have a lot of control over. Good. So one of the important things about astrophysics is is discovery. Actually, key in astronomy is discovery. We are discoverers. We discover things. I'm very interested in precision measurement and discovery, but you have to work in discovery in astronomy. And that means we're always trying to find new things. And so this train and test framework is always a tension for us. Because if you train on the quasars you know and try to find new quasars, you'll only find quasars that are in some ways similar to the ones you've already found. And then the other thing that is kind of a deep idea, and this was something we've discussed a lot, we founded the Center for Data Science at NYU, and we discussed this a lot, is that in data science, you tend to see the data as given. Like you just get the data, you get the Twitter network. Whereas if you go to like traditional physics, you control how you get the data, and experimental design is an important thing. And even in astrophysics, experimental design is very important. We decide what we're going to look at, when we're going to look at it, how we're going to look at it. We don't just get the data. We think about those design questions. So it's like, anyway, lots of things. Okay, good. So now I'm going to get controversial again. Who here would say that they've used machine learning at some level in their research? Okay, good. Smaller fraction than I'd expect, given the abstracts I see coming across my desk. Controversial, a lot of people would not agree with this. So I said, my definition of machine learning was a little controversial. This slide is also controversial. I do not believe you can ever know what a machine learning method is doing. There's a lot of people who work on interpretability and interpretable methods and try to use things that are interpretable. I even write in my own papers, we're using this method because it's interpretable. And then I feel a little dirty that I wrote that. Because I actually don't think you can ever interpret a machine learning method. And the reason is that when you have a lot of capacity, when you raise the number of features or you raise the number of parameters, or you build a lot of capacity, you give your model a lot of freedom, then it has a lot of internal degrees of freedom, often even literally degenerate degrees of freedom. And for that reason, you're never going to be able to look inside and see what it does. Yeah?
There are, I can synthetic what I'm mentioning.
Yeah.
There are machine learning methods that will at least tell you which pixels are more important.
Yes, that's very relevant. It's a follow-up thing I'm about to say. But see, were you going to say something? Yeah. Right. I mean, well, I do linear regression, right? So in for a lot of projects, I work with linear regression, and so linear regression is interpretable in the sense you get a set of weights. But once the number of features is large, like once you have 30,000 features, there's a lot of ways that the weights end up playing off against each other that when you look at it, it just does not make sense. Like if you just take the abs of the weights and rank your features, it makes no sense. And if you change your training set, you get a different ranking. So it's not like yeah. So my point of view is that just anytime you have a high capacity model, it's not going to be interpretable in the way that physicists like. It's not going to be like, oh, that's because the electron scattered off of the dark matter particle and produced like momentum. Like it's not going to be like that.
You can interpret it yourself. That's why you have to rate.
So the caveat to all of this. So the last I put this slide up in a machine learning mathematics of machine learning meeting in New York a few weeks ago. Actually, I wasn't giving a talk. It was just a panel discussion, and I just said this. And the people in the room who objected kind of on the grounds that you just said, which is that there's a different kind of interpretability you can think about, which is where you do interventions on the model. You like treat the model itself as your experimental subject, and you do experiments on it. And that's kind of the way those medical things work. They show that if you mask out this part of the image, it can't make the diagnosis. So it's this part of the image that's creating the diagnosis. So there's a kind of, there is a way you can interrogate a machine learning method. But it's not interpretability in the way physics models are interpretable. The way physics models are interpretable is you understand what every latent variable is, and you can describe it, and it's got a set of equations. That's not happening here. Good. So I think the key question is this one. Where can you use a model that you don't understand? And I think the answer is that there's lots of places you can use a model that you don't understand. Shh. Well, so one of the reasons that I think you can use a model that you don't understand often is that you don't even understand yourself, and yet you're capable of doing science. So there are places you can use. The other thing is you can build a machine, a hardware machine. Like we build hardware machines for our projects, and those machines don't ever end up doing exactly what we expected, right? We have like models of what they're going to do, and then we turn them on, and they don't do that. They do something different. So we don't understand always why they're doing something different, but we can still use them to do very good science. Very precise, very good, very accurate science. You want an example? Yeah. So when we build a spectrograph, for instance, we'll build a spectrograph and we can predict, based on our optical models, what the traces of the starlight will look like in the spectrograph focal plane. In the end, they don't look like that. They look very close, but there are differences, and the differences we can't explain them in detail. And we say, okay, we're somehow wrong about some aspect of the optical model, but often we can't even tweak the optical model and get them. We just learn empirically that's where the traces hit, and we just work with it, and we're fine. You just calibrate it out. Yeah?
On the exam way, we might want students for research on time. Nobody has defined time dilation when we don't even know the first what it means. There's no definition of anyone around this room that everyone would agree on what time is.
Actually, yeah.
We say the same thing about energy. What's energy?
Yeah.
What's momentum?
Good. That's like the comment that we don't understand quantum mechanics, but we can still use it. Like, yeah. Good. Great. Good. Good. I like that energy. Let's bring that energy to the next part of this talk. Okay. So starting off strong with things that I'm sure are a bad idea. So I think I say it in a slide or two. Say it in a minute. In a minute, I'm going to say that right now, if you look at there's very big cosmology experiments starting in the world right now. There's the Euclid satellite just launched in Europe, and the Simons Observatory is about to start taking data on the cosmic microwave background. Both of those experiments analyze their data by comparing their data to simulations. And I don't know if people know about what simulation-based inference is, but the most rigorous way to compare your data to simulations requires a very large number of simulations. Like not hundreds of simulations, like hundreds of thousands of simulations. So the requirements of Euclid and the Simons Observatory for simulations is larger than the computing capacity of the entire world right now. So literally, if the whole world said, we don't need any computing, you cosmologists can have all of it, we still wouldn't have enough to meet the goals of these projects. So that means that instead of doing unbelievably expensive simulations of the universe, people are building machine learning replicas that are emulators that do the same thing but much faster. So this is thousands of hours on a supercomputer. This is seconds or minutes on the same computer. And this is basically going on everywhere in the science. By the way, almost everywhere in the sciences now, the theory is simulations. Like if you're not a string theorist, the theory is simulations, right? The Atlas theory is simulations of the particle interactions. The ocean and atmosphere theory is simulations of ocean and atmosphere. The cosmological theory is simulations of the cosmological volume. The physics is now a simulation-based activity. Say again?
Monte Carlo.
Yeah, right. But it's Monte Carlo plus immense physics computation, both. So in almost every area, people are moving to emulation, including climate science, which is pretty important to like the future of humanity. Yeah.
Just the observation as well, or is that what you can't? That all of it, that's what you can't tell.
Yeah, I was going to say the prediction doesn't match your simulation.
So the crazy thing about this is you have data, you have simulations, and then this is just a prediction of the simulation. It's not even a prediction of the data yet. So there's two hard things here, comparing the simulated world to the real world and making a faster version of the simulation that you believe. Both things are in play. I'm only talking about the emulation part here, but actually I work on both sides of that. I also work on taking the fundamental data we use here. So I work actually on every part of the cosmological chain. Anyway, I think I've said enough there. Who here has seen this picture before? A few of you. Okay, so this is an extremely famous result in machine learning, and it's from 2015 here. I mean, these ideas existed before 2015, but 2015, if you look if you look at citation analysis, like this concept blows up in 2015, and now it's like a big part of machine learning. And it is that whenever you have a model with an enormous number of free parameters, it has really weird pathologies. Basically, it has to, because your model has so many degrees of freedom, it's going to have things hidden inside the model that you don't know about. You kind of, in the same way that the model isn't interpretable, it has properties you can't know. So what's the experiment here? So this is an image from, I think, ImageNet, but I'm not sure. It's one of the standard, there's a bunch of standard image data sets that are used in machine learning for training models, and there's competitions. And this attack was done against one of the competition-winning models. There's competitions every few years for labeling images. And here's an image from the database that the well-trained model predicted with 57.7% confidence was a panda. And what happened here is in this paper, they very, very carefully searched. This is not a random perturbation. This is a very carefully constructed perturbation. And it's tiny. Look at the amplitude on this thing. A tiny amplitude on this perturbation. And that produces this image. This is the image that's produced after the perturbation. So you can look at this image and see what you think this is an image of. But I can tell you that at 99.3% confidence, it's a gibbon, which always makes everyone open their phone and search for gibbon. Actually, so I shouldn't say this because this now derails the conversation, but I believe that what's going on is that somehow by adding this noise, it's reading this as the animal, because that looks like a gibbon. You got a gibbon up there in the back? That's a gibbon, right? See, doesn't it look like that? You see, couldn't that be the face of a gibbon right there? Anyway, I don't know what's going on, but so there's many attitudes you can take towards this. This is a very interesting thing. This led to a huge literature. So this paper, the first paper, kind of took the view like this shows that it all crap. But then lots of papers came in that said, no, this is an expected behavior. This is a feature, not a bug. And I'm like, okay. But the thing that I take from this is that the machine learning method is not doing what you and I do when we look at this and say, yeah, that's a panda. I don't know what I do because I actually don't have an interpretable model of my own brain. There's probably some deep philosophical reason you can't. But anyway, Wittgenstein had things to say about that. But I think of it as like there's eyes and ears and it's got a white face and black features and it's in a tree. That's seeming very panda-like. And then there's some additional things, snouty things and fuzzy things and stuff. I'm like, that's a panda. This looks very similar to me.
You were saying that you were thinking that it's interpreting the nose as an animal, but can you tell?
You can't even tell. Actually, you might be able to tell because now there's much more sophistication in telling. So it'd actually be very interesting to take this image and interpret where the features are dominant and take this and interpret. That's probably been done because there's such a big literature on adversarial attacks. Like there's more papers on adversarial attacks per year than there are papers on astrophysics. Machine learning is a very big field. So every subfield of machine learning is bigger than astrophysics. And we have like 5 journals. Anyway. Okay, good. So what do the adversarial attacks reveal? I don't know, but I believe that they don't represent generic failure modes. That was a very specifically chosen thing. And there's all sorts of other adversarial attack approaches out there. But they reveal to me that the model isn't doing what we think it's doing. And you see the relevance of that when you put a machine learning model into astrophysics problem or a physics problem. Now you're introducing some things, some modes, or some behaviors that you know are physically wrong.
So how was that specific noise calculated?
It's very nice, actually. This one was found, they basically tried to move this image in a direction that what no other image they'd ever seen was. So like they were trying to move this image away from all images they've ever seen before. That's more or less what the attack is. So somehow this image is very generic and this image is very non-generic.
Okay. I almost understand.
You can get this hypothesis that you were just making that the probability of machine learning algorithm was inherently known. Because they would have just removed the noise from the model.
Right, so then I would have expected there would be some localized thing here, but there isn't, yeah. But of course the model's very nonlinear, so it's possible that weird combinations of this tell it to look here. We don't know.
Like if you look at the anisotropies of the CMP,
Yeah.
you can't really tell they're all those
Yes.
peaks.
Yeah.
If you look at that, if you did something to it, you could come up with something regular.
You mean you could Oh, this. Yeah. No, there's a lot of interpretation of this. Actually, there's many papers that interpret this, which is out of scope for me because I'm just using this to say we don't know what's going on. But there's a lot of structure here for sure. Yeah. Okay, good. Now I want to make the first. I said I was going to make 2 technical statistics points. This is the first of the technical statistics points. So the simulations are incredibly expensive. Right? And that's true. The 2 fields that I'm looking at right now are cosmology and ocean science. And in both of those fields, as I just said, the requirements exceed the computing capacity of the US or the world. If you really wanted to compute the oceans at the level we would like, you would need all the computing in the world and it still wouldn't be enough. So you use emulations as your theory. Now imagine you find something really surprising, like the sum of neutrino masses is less than the lower limit from the neutrino mass splittings, or whatever. Or maybe you find that global warming is going to reverse and it's going to be a new ice age. I don't know. You find something very surprising. Now, what do? Just publish and go, good, we're good. We found this really good discovery, give us the Nobel Prize. Probably what you do is it's surprising, so you go back and you check with real simulations. But if you go back and check with real simulations, by construction, that is overwhelmingly expensive. That's why you didn't do real simulations in the first place. So you have set yourself up for absolutely insane confirmation bias. So we may be putting ourselves in a bad place in terms of coming up with correct inferences about the world.
So you're saying that something wildly different than you're not thinking, but it's just a little bit different. You go, okay.
You'll be like, cool, that's good. Yeah, we'll be like, neat, we found something. People get their PhDs, people get their tenure. Mm-hmm. Yes, right, yes. That is somehow related. That I would say that's off topic, but it's not off topic. The confirmation bias is that you only check the results you aren't happy with. So a standard thing that most people in this room do is they write their code and they try to run it and it gives weird results, and then they look for bugs and they run it and it gives weird results. They look for bugs, they fix them, run it again, still weird. Look for bugs, find them, run it. Oh, it looks good. We're done. Stop looking for bugs. Yes.
That's not what I do. What I tell my students is that you have the right answer. That means either you're right or you have an even number.
Yeah, exactly.
So then I always tell them, go to after you've gone to n, go to n plus 1. Try to break it now. And if you successfully break it, then you're not done.
Yeah, good. I agree with that strongly. And actually, one of the experiences that probably everyone in this room has had, I've had a million times, is something's wrong with your code. It's totally wrong. You search through your code and you find a line of code that is so disastrously wrong, you can't even understand how your code ran at all. And then you fix that line of code and then you run your code and get exactly the same answer. And that shows you... Right, that's sometimes what's going on. But anyway, that experience alone tells you that there's a lot of confirmation bias going on. And in general, as you get more and more separated from your subject, you're more and more likely to be in this space of confirmation bias. I have a million things to say about that. I'm not going to say about them. By the way, I don't have a solution to this. I'm not setting up this problem to say, here's how we're going to solve it. I literally don't know. I think we might be in bad shape. Okay, good. Now I'm going to talk about a standard problem in astrophysics. I guess, how am I doing on time? Not ridiculously well, so I'll probably skip some parts of this eventually. But one of the things that is a very important problem in astronomy right now is to infer the mass, age, and composition of all the stars that we see. And there's this Gaia mission that's taking data on a lot of stars, and there's a kind of theorem, it's almost a theorem in astrophysics, which is that once you know the mass, age, and composition of a star, you know everything about it. You can predict everything about a star from just its mass, age, and composition. Now that isn't quite true because there's some angular momentum and some magnetic field and stuff, but really the dominant things are these three things. And of course this one is a high dimensional thing. It's like the amount of different elements. But it really is very finite what you need to know about a star. So this is a really nice problem. And it's hard to do, and right now the standard classical ways to do it involve a lot of computation because you have to forward model the star with a physics model of the star. So a lot of what is going on is that there's a few stars that have been very carefully modeled and analyzed, and then we use those and regression with machine learning to label all the other stars. And the Gaia mission is the key mission right now, and it's delivered data on 1.4 billion stars and spectra of 200 million, 230 million. And so it's really a big deal right now. And I've worked on this problem a lot. This is one of the things we worked on. You can't really see this slide from the back, but there's a gray line on these slides. This is 4 different stars. The gray line in here is the data, and the blue line is a model that's generated by machine learning. It's a machine learning model for the spectrum. So this is like a generative model for stellar spectra, and we were doing it before it was cool. That's 2015. This model was designed, actually started as an information theory question, like where is the information about mass, age, and composition encoded in the data? That's what we were doing with this model, but then it turned out to be a way to label stars, and we used it to label stars. And there's a lot to say about this. I'm really just throwing it up here to show that this is the kind of problem we work on. And you can see that these spectra have tons of information in them, and we can model all the lines very well. And this is a tiny piece of a spectrum. I don't know if you can see this. This goes from 16,160 angstroms, because we're astronomers, 16,160 to 16,280. So this is just a tiny little piece of a huge spectrum of the star. This is like 1/1000th of the spectrum that we have.
Second down on the right, there seem to be blue lines, which is the model, right, in regions of the spectrum which are not appear to be gray lines.
I know. One of the things that's cool about this model, because it's a generative model, it can make predictions even where there aren't data. And by the way, there were data in the training data. These are not in the training data. So these are ab initio predictions. So these stars are predicted by the model. And so this is a star that didn't have data. It has a data gap here, but this star has data at that location. So things in the training set had data at this location, but this star didn't. So we actually are making an actually hard prediction there of what the star would have looked like if we'd seen it, which is testable. Actually, this star probably has been reobserved, so we probably have it now. I haven't checked. That's a good question. I haven't checked. Blah, blah, blah. And these models are getting very, very sophisticated. This is a recent paper we just wrote, and the only reason this is up here is to say things are complicated now. That's the only message here. But one of the things that's very interesting is we found that if we want to learn, these are parameters related to the mass, age, and composition of the star, and we've learned that if we want to learn these things, it helps to predict other things, like to predict many things at the same time. Somehow we've learned that machine learning models are better behaved if they predict more things than you need. And we don't understand why that is exactly, but it has something to do with constraining the latent structure of the model. Anyway, that's off topic. Okay, good. I'm about to make another one of my technical statistical bias things here. Okay, so this is now, I'm in Albany now, so that now I'm like have to get a little careful here because I'm about to say something that touches Bayesian inference. And I do a lot of Bayesian inference. So I feel confident that I can say correct things, but I just don't want to offend, well, I want to offend some people in the room, yeah. But anyway, one thing that is very important idea in Bayes is that if you want to do a joint analysis of multiple objects, you want to combine their likelihood functions. You don't want to combine posterior information, you want to combine likelihood of the objects, not posteriors. And the reason is that you have you've done multiple analyses of objects with priors, and you don't want to multiply all your priors together. You just want to multiply the likelihood functions together. So this is just an important, like, basic point in statistics. You multiply likelihoods together and not posteriors. The danger is that machine learning regressions tend to reproduce things that are much more like posteriors. They are much more like posterior quantities. So if you do a standard machine learning regression, like with a multi-layer perceptron, the output it's giving you is something like maximum a posteriori under a prior, which is your training set. Good? That is not quite true, and actually there's a big technical literature about that question, but it's close to true. Good, so now this is the kind of problem we do all the time. You have 1,000 stars in some part of the galaxy, the outer galaxy, you have 1,000 stars, you've found them, they're really interesting stars. Now you want to know what is the mean age of those stars. So what do? We take the ages we have for those stars and we average them to get the mean age, or maybe we take the median of them to get the median age, whatever. But if there are maximum likelihood estimates of the age, you get a good estimate for the mean age. But if they are posterior estimates of their ages, you get a very bad estimate for their mean age. It's just pure stats. And so we are in a danger now, and I think I make it clear? Yeah, no, this is my main point, is that if you're averaging posterior estimates, it's like you're taking your prior PDF to the 1,000th power. Because you had 1,000 stars and you multiplied them together. So this is generally very, very bad. This is not a good idea. You don't generally want to take your prior to the 1,000th power. Almost any prior becomes a delta function when you take it to the 1,000th power. And so machine learning outputs are not actually useful for a lot of scientific tasks that we do. Yeah? Correct. Correct. Good. I agree absolutely completely. So the key thing is, when you are, if all you care, so this is the big thing, the key thing, and this actually applies to a lot of things, even outside of machine learning. It applies to a lot of things that are probably happening in this department. Certainly in my 2 departments, a lot of things. If what you want, if you are measuring the ages of stars because you want to know the individual ages of those stars, you definitely want a biased estimate for all those reasons that you just said. Because because you do have biases and you can lose variance in exchange for that bias that you take on. So you do want biased estimates. But if you were then doing a population estimate of those objects, you want to know something like the histogram of the ages, which is a population estimate, then you do not want that bias unless you have some way you can remove it at the end. But usually you can't remove those biases at the end. So it depends on the use case. And so the machine learning methods are literally designed to answer what is the best ad to show you. If you want to know what's the best ad to show you, you want a biased estimate. Because it's conditional, and B, you want low variance. So you're going to show a biased estimate. But if you wanted to do anything population estimate over ads, that would be bad. Again, I have no solution for this problem. I think this problem is deep and problematic. There are some methods, actually the canon that I showed is a maximum likelihood method. There are some machine learning methods that are maximum likelihood, but they're unusual. There's some kind of there's some kind of like frequentist hierarchical things that are machine learning methods, but they're maximum likelihood. Okay, good. I just want to say a couple things about causal inference, and then I'm done. We don't often talk in physics about causal inference, but if you go to statistics department, or if you go to medical, or if you go to education, people are all talking about causal. Like, does policing in neighborhoods affect how children perform on school tests or whatever? Like, it's really about causal relations. And we don't generally talk that way in physics because we have a kind of very rigid causal model. But in astrophysics and in things like the LHC, it does come up because we ask things like, was this feature of the data created by the star that we're observing, or by the atmosphere that we're observing through, or by the instrument, which is like varying and changing its temperature? So this is fundamentally a causal question. Can we see where the features in the data came from causally? And this is a big area of research in machine learning now, and it's very relevant to problems we work on. And so like in my case, I work on things like we measure the brightness of a star very accurately over time, and it does vary, and actually in many cases the variation is dominated by our instrumentation, not by the star. And we make these separations. But one of the interesting things is if you want to say that you successfully separated the star and the instrument, and you can say what variation came from the star and what came from the instrument, your argument is most convincing if you gave the instrument a ton of flexibility. Because if you didn't give the instrument very much flexibility, obviously it'll say, oh, well, all the variability is coming from the star. But if you want to be very conservative about what came from the star, you want to give a lot of flexibility to your instrument. And a lot of flexibility should make you think machine learning. That's like that's what it's about, making very flexible models. And importantly, often we don't need to interpret our instrument models. That's what I was talking about earlier. Our instruments will sometimes have properties we never understand, and we don't care. Which? Meaning, well, maybe this will help. This is the measurement of the brightness of a star over time. And this is from the K2 mission, which is a NASA mission that happened at the end of the Kepler's lifetime. And the green line drawn through here is our prediction for what the instrument was doing. So notice the green line is doing crazy stuff. I don't know if you can see the green line in here, but there's a green line that's going up and down, and this is the difference between the data and the green line. And this is measured in parts per million, so this is like a really, really quiet star that's barely varying, and we get it down to 35 parts per million, so it's 0.00035 is the RMS of the variation. But this model for what the instrument was doing requires a lot of flexibility because we're letting it do this crazy stuff. So that's what I mean by flexible. We don't think the star was doing this. We think the instrument was doing this. And this is a prediction for a star that was not used in the training set. This is like an ab initio prediction. Anyway, the argument, this is an example where by the way, this is a really bad, luckily I'm out of time because this is a really bad example for me because this variation that you see here is actually completely interpretable. These are thruster firings of the spacecraft. It turns out this model is perfectly interpretable, and the fact that this part looks like the opposite of this part, you see this? See that? That's because on this side, the solar torque was in one direction, and on this side, the solar torque was in the other direction. Like, this is completely interpretable, which totally undermines my whole talk. So I'm not going to say that. And I have other examples. The most famous foregrounds and backgrounds is this microwave background. You see the microwave background through the galaxy, those separations. Another kind of separation, this is a stellar spectrum, and this is the absorption due to the atmosphere. This is the absorption due to the star. This is the spectrum you see. So this line here comes from the atmosphere, but this line comes from the star. This separation into these two components was done totally data-driven. There's no theory in here. Anyway, we have lots of things like that. Good. So the open question I'm ending with is I'm going back to emulators because I like to end a talk with an open question, something we don't know how to solve. I actually brought up two statistical problems, the confirmation bias problem and this joint analysis kind of problem. But an open question is how could we get to the point that we trusted these emulators? It's something we talked about over lunch. We don't know the answer. Right now, the problems that we're working on in my group, this is with Soledad Villar, who's at Johns Hopkins, who's a mathematician. She and I have been jointly advising graduate students working on questions about exact symmetries. Is imposing exact symmetries like physics symmetries, like diffeomorphism symmetry and rotation and translation type symmetries, or conservation laws? Would that help? Adversarial training, like I showed the adversarial examples. Does adversarial approaches, are they going to create trust? Could we produce sanity checks? Like when a graduate student produces something, we ask them questions about it. Could we do the same kind of asking questions? I don't know. We're thinking about that too. Anyway, one of the interesting things is this connects to like the bigger debate that's happening in the world, right, about X risk. And if you don't know what X risk is, good. I'm done. Thank you.
In terms of the emulator questions,
Yeah.
it seems like there's two paths here, and one of which is to try to find ways to make the simulations less expensive.
Yes.
And so there are coarse graining
Yeah.
techniques or the equivalent, which do,
Yeah.
impose some physics or whatever
Yeah.
science
Yeah.
on saying, I don't need to know what every molecule in the ocean is doing to produce.
Yeah, right, yeah, yeah. Good, so I have a million things to say. I could give like a course on emulators because there's so many different ways to emulate. In fact, the thing that people are interested in the oceans is actually not fully replacing the simulations with machine learning. It's to make the simulations way lower resolution and fill in all the detail with machine learning. That's more what people are thinking about in that area. So emulators can mean a lot of different things. Like one kind of emulator is just to try to learn a high order integration scheme. So instead of doing like first order, like Euler's method, you could be doing something much higher order, and you could just learn that. So that's one meaning. Another meaning is fully replacing the end-to-end simulation, which is what they did in that cosmology project. Another one is running at low resolution and filling in the details. That's the way the oceans people are working. And another is sometimes you don't actually need the whole simulation, you just need certain statistics from the simulation. And in that case, it's often easier to simulate the statistics than to simulate the whole solution, the whole simulation. You can emulate the statistics that come out of the simulation. So there's like lots of different approaches, but I think they all have these trust issues. Even like coarsening, the crazy thing is, as we were working through all these ideas we had for improving trust, we realized we actually don't trust the actual simulations either. So it turns out the ocean simulations don't obey the standard conservation laws. So like sodium ions are being created and destroyed at every time step in the ocean simulations. They don't conserve salt. There's other conservation laws they don't obey. So we're actually also thinking about the question of like, could we also apply whatever we learn here to actually directly to the simulations? Like, could we make the simulations exactly obey symmetries and so on? And that also might help with the coarser grain, like the coarse simulations might be more violating the conservation laws. And so maybe by forcing them to exactly obey the conservation laws, maybe we can improve the coarse grain. So there's a lot of different approaches. And whenever I give this talk, people always say, well, why don't you just make better simulations? And I'm like, yes, great idea. Go do that, yes. I strongly support that. That's way better than learning about machine learning. But right now, one of the reasons we're driven to this is that a lot of the PDE world feels really stuck. They really don't know where to move. Yeah.
So earlier in the talk, you mentioned that maybe some of the problems were developed from a commercial standpoint.
Yeah.
If we had sort of huge amounts of resources and a scientific community we redevelop
Yeah.
machine learning, would that ameliorate
Yes, 100%. I mean, if you look at, so AlphaFold, so DeepMind did two really impressive things. They did several things that are impressive, but I think the two really big ones are AlphaFold and Go. So DeepMind DeepMind plays Go, like not just better than any human, but like more creatively than any human. The Go masters were like, whoa, there's new strategies here we hadn't seen. And in both of those cases, if you look at the author lists on the papers, they're immense. And those people are being paid 400 grand a year. So yes, if you give me a team of 250 people with $400,000 a year salaries, I promise you, I hereby promise the American people that I will solve these problems. I'm joking around, but really, like the money that's being spent on the commercial side is immense. It's not like, oh, they're a little bigger than we are. Like they could buy us. Like the combined machine learning communities could buy astronomy. And so, and I think if you put all of that brain power, when you go visit those companies, I do visit those companies, they're in New York, and some of my friends work at those companies, and when I'm sitting in on the meetings in those companies, they are thinking in a very sophisticated way. Like Google Ads, the way Google puts ads on search results is really well thought out. That's not we'll just throw some ads at it. Like there's a really serious piece of engineering behind that hundreds of extremely good engineers and computer scientists and even theoretical physicists contributed to. So these things are really well instrumented by people. And I do think like, okay, cosmology, I can make fun of it, but ocean science, actually, we can't make fun of anymore. It's literally existential threat to humanity. So I would love it if DeepMind decided to put the attention that they put into playing Go into predicting the climate.
Go more complicated than chess, I'm not familiar.
Go has way wider strategy space than chess, yeah. It's a more interesting game in a lot of ways, I think. Because chess is all about look ahead, whereas Go is more like in the moment.
Yeah, never played it.
But by the way they solved that Go thing was so interesting, and I think it has some implications for us. The way they solved it is they made different agents that played Go against each other, theoretically inside. They didn't train it. It wasn't based on training data. There was no training data. They just had agents that knew the rules that played each other, and they just duplicated the agents that were doing well and killed off the agents that were doing badly, and eventually they had a set of agents that were really good at playing Go. So maybe that has implications for science. I don't know. Were you going to say that?
I just mentioned that there was this paper by Klaus Shannon, I think, where he assumed some reasonable assumptions, and then he calculated that the number of chess games is not more than 10 to the power 120. I'm pretty sure that Go has much more.
Has far more games. That could be, yeah. Go is a very flexible thing. It's got exchangeability, right? Exchangeability, that's a serious symmetry. Yeah.
So you had started talking about the lack of discoveries, and I'm not sure if that's the right metric.
Good. I'm sure it is not, actually.
Yeah, so I heard a talk by Neil deGrasse Tyson once where he said that machine learning, he likened it to a tool. I'm not sure how fully I agree with this, but it's a tool in the same way as calc when we invented calculus,
Yeah.
statistics. And you're claiming that machine learning has made discoveries. You could actually make the same case with calculus. It's a tool.
Yeah.
It doesn't make the discovery on its own.
That's right.
Until machines become sentient.
That's right.
It's unfair
Good.
to expect
Good.
So like, for example,
Good.
by dark matter,
I'll agree, yeah.
machine learning, not because we think it's going to help us discover dark matter, but because it's going to save student time.
Yeah.
For example, to be able to do the instrumentation.
Yes, exactly, yeah.
Pointing out, knock that out so that the students can focus on things
For sure.
only a human brain can currently
Exactly. Good.
and do the harder work, the
Yeah.
creative work that
Yeah.
AI is still incapable
Yeah.
of really doing, ChatGPT notwithstanding.
Good. I agree with that very much. And of course, in fact, in that same Twitter thread where I said, like, what is it found? And I said, I'll go first because one of the first, what I would call machine learning systems in astronomy was the system that measured the redshifts in the Sloan Digital Sky Survey. So the Sloan Digital Sky Survey, which we did I've been involved in Sloan Digital Sky Surveys all through my life. We're now in Sloan Digital Sky Survey 5. I'm the chair of the advisory council, which is my project management joke earlier. But in Sloan 1, in the first Sloan survey, we took 1 million spectra and we had to measure the redshifts of 1 million galaxies. Well, no one knew how to do, like when I measured redshifts as a graduate student with a ruler, like the way you do. That's how I measured redshifts. So we had to automate that, and that automation was done with something like PCA on the objects with known redshifts, and then did like translations and PCA combinations. So it was linear combinations and translations was how we measured all the redshifts. And that enabled all of the science of the Sloan Digital Sky Survey, which we discovered the baryon acoustic feature in the large-scale structure and nailed a bunch of the cosmological parameters. So like it demonstrated the flatness of the universe. Like we did a lot of very important things with that. So you're right that that's the wrong way to think about it. The right way to think about it is it contributing to the whole scientific enterprise? And I think the answer is undeniably yes at this point. And I think I did say that.
You did. You said engineering. And yeah, engineering is a good way to think about it. Because it's not, you know, we knew the equations for that would govern airplanes for centuries.
Yes.
Yes. Is definitely separate from physics, but is a valuable foundation that every enterprise
Yeah.
has. So.
That's right.
One thing that one can say about calculus example is that we know how calculus works.
Yes. Yes. That's a difference. That is a difference. But we do use some tools that we don't know how they work. Like for instance, I write all my code through an interface known as graduate student. And after all these years, I still don't know how it works. They're really good though. They're way better than I am. Well, I also use postdoc, but they have way more issues. Yeah. Yeah. I view PCA as machine learning, but the most simple form of machine learning. So for me, I really love the things I really love are PCA, linear regression, and nearest neighbor. And whenever we do a machine learning, like a real machine learning thing, we always baseline against those techniques. And oh, that's the crazy thing. If you carefully tune nearest neighbor, we find that a tuned nearest neighbor often beats a tuned like deep learning thing, or is equivalent or beats. So like if you put a lot of effort into those basic things, they actually do extremely well. So a lot of the really good ideas of machine learning have actually been around for a long time.
Well, I mean, it's not really machine learning.
That's the question. I opened with my maximal definition. In my maximal definition, it is machine learning, but you're right, that people literally split. So for instance, when I showed you that Cannon model where I showed the cyan line on the gray line of the stars, the first author in that is Melissa Ness, who's at Columbia, and she is adamant that that is not machine learning. And I'm adamant that that's a great example of machine learning. So we literally, and we're co-authors on the paper, and we don't agree on whether it's machine learning.
I have a question about, so you come from NYU, right? So there's another prominent figure, Gary Marcus.
Yes, I know him well.
Who is very well known for his state that you should be very conscious of artificial intelligence. Thought that are the majority of faculty share that view?
Oh, that's a great question about a lot of that conversation is about there's several aspects of that conversation. There's kind of a conversation on what used to be Twitter that is about a mix of things that includes machine learning sucks and machine learning is going to kill us all. And oddly, the people who believe that machine learning sucks also seem to believe that machine learning is going to kill us all. And then there's another group of people who are like, machine learning doesn't suck and it definitely won't kill us all. And I don't like either of those points of view, so I think it's very divided. In fact, it's a great thing, like when you're having lunch with people who work in machine learning, is to bring up whether the machines are going to kill us all, because it'll turn out. Because first of all, yeah. I mean, there's a lot of reasons it's a good thing to discuss. But actually, what I found is it's very surprising how much diversity there is in that whole area. I am actually slightly interested in it because I mean I would welcome our robot overlords personally, but because I think that scientific questions give us a little playground for thinking about how do we understand, trust, and control the machines we don't understand. So this is like a nice, safe playground to think about some of the things which do come into X risk type question. So that isn't an answer to your question. I don't really know where everyone sits. I do think a lot of people are very worried that computers are going to take over and kill us all. But anyway, one of the things that people like to say is that it's undeniable that eventually machines will be smarter than humans, like more intelligent than humans. Like, I agree with that. I think eventually we'll be able to build very intelligent machines. I think that's probably likely. But then it's worth pointing out that right now the world is not actually run by the ones who are most smart. So now I don't know which way that plays. I'm not sure whether that's a good thing or a bad thing. But right now the machines are not looking a lot less ethical than the humans. Anyway, yeah. I think it is like.